Hi, I'm Jesse, and today I'll be talking about constructing improved extractors for small space sources. This is joint work with Ishan Chattopadhyay. So randomness is a really powerful resource. It has some great applications in algorithm design, cryptography, combinatorics, distributed computing, and in Monte Carlo methods. But most of these applications require access to uniform random bits. And the actual bits that we can find in the wild often have unwanted correlations and biases. So we'd like to construct some sort of device that can purify these weak sources of randomness. Well, this device is exactly an extractor. And we model our perfect randomness by uniform distribution, and we model our weak randomness as a different distribution coming from some family of known distributions. So formally, an extractor is defined with respect to this family of distributions and some error epsilon, and it gives a guarantee that given as input any random variable from this family, the extractor will output bits that are epsilon close to uniform in terms of statistical distance. Now, a key property that we want of our extractor is that it should be explicit in that it should be efficient and deterministic. Moreover, we'd like to output as many bits as possible, but to keep this talk simple, let's focus on outputting one bit. And of course, we want the error of the extractor to be small. So the question then is, what should we pick as our family of distributions? Well, maybe the most obvious answer is we want to make it as general as possible. But in order to extract any randomness from it, of course, every distribution in the family needs to have some randomness itself. And we model that with min entropy. So we say the distribution has min entropy k if it hits any value in its support with probability at most 2 to the negative k. And this value ranges between 0 and n, with the closer it is to n, the more random the source is, and the easier it is to extract from. So given this, the natural question is this enough? Can we just try to extract from all sources that have sufficiently high min entropy? Fortunately, a classic impossibility result says no. Even if the sources have super high min entropy, it's impossible to extract from them. So given this impossibility result, researchers have considered a variety of different directions. And in this paper, we focus on adding some sort of computational structure to the source called sampleability. So in particular, we continue a line of work initiated by Trevisan and Badhan on extractors for sampleable sources. Now, to motivate these things, remember that we're getting bits of randomness from nature, and it's natural to maybe ask, is nature equipping these bits of randomness with some sort of structure? Well, it's not too far-fetched to argue, and some people have argued that perhaps there are actually perfect uniform random coins out there in the universe somewhere, and the bits that we're observing in nature are just computationally bounded algorithms applied to these perfect coins. So these are exactly what sampleable sources are. So people have studied this in the setting of small circuits, time-bounded algorithms, and space-bounded algorithms. And if you're not completely sold on the kind of philosophical motivation, I should note that this is a pretty natural family. It generalizes many previously studied models, and it also has connections to a nice new emerging area of complexity theory. So in this work, we'll focus on extracting from sources generated by space-bounded algorithms, in particular, small space sources. So a small space source, again, is generated by a limited memory algorithm, or rather an algorithm that has just S bits of memory. We model this thing by taking a random walk over a branching program of width 2 to the S. Now, a branching program is just a layered DAG with n layers and width 2 to the S, and an additional designated start vertex. Each internal node is allowed to have an arbitrary number of edges going into the next layer, which it labels with output label 0 and 1. It also assigns a probability distribution over its outgoing edges. Now, a small space source generates a sample by taking a random walk over this branching program, starting at the start vertex and using the transition probabilities and printing the output labels it sees along the way. So this has been studied in several previous works, and it turns out that it actually generalizes a lot of well-known models. So our goal in this work is we'd like to construct improved extractors for small space sources. In particular, we'd like to minimize the entropy requirement. So in our first result, we construct near optimal extractors in the polynomial error regime. Previously, the state-of-the-art extractor was able to extract from min entropy, whose dependence on n with some small subpolynomial term. So we improve this to a dependence that is just polylogarithmic in n. So in the natural setting of setting the number of bits to polylogarithmic n, we improve the entropy requirement roughly exponentially. However, while polynomially small error is enough for a lot of applications, it's not for some settings like cryptography, And so our second result focuses on constructing improved low air extractors for small space sources. So here, the previous state of the art was an extractor that extracted from roughly n to the 2/3 bits of min entropy. So we improve this result to a dependence that is n to the 1/2. So you might be concerned that there are kind of varying powers on this term S, but I should note that this is a strict improvement because we can always assume S is at most n, otherwise extraction is impossible. And we can actually usually assume S is much, much smaller than n. So in the very reasonable setting of setting S to n to the 0.01, we achieve this improvement here. In addition to our improved extractors for small space sources, one thing that I think is cool about these constructions is that they depend on a lot of interesting objects and reductions. In the remainder of the talk, I'll overview our two constructions, and I'll give a whirlwind tour of some of these objects. We'll start with our low air extractors for small space sources. And here, the first ingredient we need is a reduction from small space sources to so-called adversarial sources. Now, before I tell you what an adversarial source is, I should tell you what a reduction means in the setting of randomness extractors. So formally, given two families of distributions x and y, we said that the family x reduces to the family y if for any distribution in x, it can be written as a convex combination of distributions from y. And formally, what we mean is that x can be written in the following form, where it samples from distribution yi with probability pi. Now, the key claim here is that if you can show that the family x reduces to the family y, and you have an extractor for the family y, then you automatically obtain an extractor for the family x. And this is a key paradigm that's used throughout research on randomness extractors. So now let's move towards defining adversarial sources. So these things were defined in 2020 in order to generalize the classic independent source model, and in order to have applications in cryptography, such as generating a common random string. So formally, an NK-NK adversarial source consists of big N independent sources over n bits. But the catch is that only big K of them are guaranteed to be good, and that they're the only ones that have any sort of guarantee on min entropy. The other ones may be bad in the sense that they may have no min entropy at all. So now we'll move to show that small space sources can actually be reduced to adversarial sources. And here, what we want to show is that any small space source can be written as a convex combination of adversarial sources. So to do so, consider the random walk that generates the small space source, and consider conditioning on that random walk hitting this exact vertex. Well, it turns out that if you do this conditioning, the small space source actually gets separated into two independent parts. And moreover, if you consider all possible conditionings of the vertices hit in this layer, you'll actually see that the small space source is a convex combination of independent sources. And furthermore, the two independent sources only have about s bits less entropy than the original source due to the entropy chain rule. Now, more generally, we could think about conditioning on hitting a sequence of nodes across R layers. And using the same argument, you can show that X is a convex combination of a sequence of R independent sources. And again, using the entropy chain rule, we can say that the entropy has only decreased by about R times S bits with quite high probability. And using an averaging argument, you can now ensure that at least a few of these should have some min entropy guarantee, meaning that they are in fact adversarial sources. So given our reduction, the next goal is to construct our improved extractors for adversarial sources, which we use two new objects. So in more detail, we'd like to construct low air extractors for NK-NK adversarial sources, where we'd like to minimize the number of good chunks required. We'd like to minimize the entropy required of those good chunks. So the previous state of art in this setting was constructed by Chattopadhyay, Goodman, Goyal, and Lee. And they're able to extract from adversarial sources that contain just root n good sources, each with just polylogarithmic min entropy. And it's actually through these adversarial sources that the previous state of art in low air small space extraction was established. And here the authors were able to extract from small space sources with min entropy roughly n to the 2/3. So in this work, we construct significantly improved and simplified extractors for adversarial sources. We're able to extract from just n to the 0.01 good sources, again, with just polylogarithmic min entropy. And it's through these adversarial source extractors that we obtain our low air extractors for small space sources, which can handle min entropy n to the 1/2. So in the remainder of this section, I'll overview our construction of these extractors. So in order to start, observe that an adversarial source is just like a sequence of independent sources, except the good sources are hidden. And so if we want to extract, we need to somehow find them. So building on the work of Chattopadhyay and Lee in 2016, Chattopadhyay, Goodman, Goyal, and Lee had the idea of using a low error 3-source extractor, which is guaranteed to output uniform bits if it's given 3 good sources. And their first idea was just try applying it to all triples. Now, the reason this is a good idea is because as long as you have just 3 good sources, one of these 3-source extractor calls is going to be activated and is guaranteed to output uniform bits. But the problem, of course, is we don't know which of these 3-source extractor calls it is. And furthermore, the actual outputs of the 3-source extractor calls can have some sort of adversarial correlation. So there's no obvious way to combine them in order to produce a single uniform random bit. In order to get around this, the authors had the idea of applying the 3-source extractor over the hyperedges of a very special hypergraph. So what they do is they lay a node on top of each source, and they're going to use hyperedges to indicate 3-source extractor calls. And the special hypergraph that they use is a partial Steiner triple system with a small independence number. And using this hypergraph, they're able to carefully control the correlation and actually extract from big N to the 0.51 good sources. But it can be shown that using 3-source extractors in Steiner triple systems, you actually can't do any better. So the goal of our work is to somehow circumvent this barrier by introducing 2 new ingredients. So the first ingredient we use is a leakage resilient extractor. So this is just a function with an extractor property and a robustness property. The extractor property says that if you give it R good sources, it will output uniform bits. And the robustness property says that if you have leaks on the inputs to the leakage resilient extractor, and each leak only depends on S-1 or fewer of the inputs, you can safely fix these leaks and it actually doesn't affect the output of the leakage resilient extractor. That's the robustness property. So the second object we use is called the combinatorial design. And so more formally, an NRS design is just a hypergraph where all the edges have size R, and you're given the guarantee that 2 edges intersect at most, or fewer than actually, S points. And so in this work, we construct a new general framework to extract from adversarial sources. So we start off by, as usual, representing each source as a node. And then we're going to use our NRS design, and we're going to draw the hyperedges around our nodes. And then for each edge in our design, we're going to call a leakage resilient extractor over the nodes, the sources it's containing. And finally, we're going to XOR the output of all the leakage resilient extractor calls. And it turns out this works. And in order to see why, observe that if some leakage resilient extractor is given only good sources, using its extractor property, it's guaranteed to output uniform bits. And furthermore, by combining the robustness of the leakage resilient extractor with the bounded intersection property of the designs, you're guaranteed that these uniform bits are actually independent of the outputs of the other leakage resilient extractor calls. Thus, we can safely XOR everything together and our uniform bits will preserve to fit. And finally, we're guaranteed that some leakage resilient extractor will actually be completely full of good sources as long as the number of good sources exceeds the independence number of the hypergraph. So given all of this, in order to instantiate our framework, all we need is an explicit leakage resilient extractor, which was recently constructed. And we also need an explicit NRS design with small independence number. So one key thing that we construct in our work are these explicit NRS designs. And so this gives the first de-randomization of a result by Rodel and Sinajova. And these are constructed by taking Hamming slices of BCH codes and using recent arguments from additive combinatorics. And so by combining these 2 objects, we obtain our improved extractors for adversarial sources. So that completes the construction of our extractors for adversarial sources and also our low error extractors for small space sources. So given our improved extractors for adversarial sources, applying this known reduction, we get our low error extractors for small space sources that can handle min entropy roughly root n. And it turns out there's actually a barrier at this min entropy root n. And if you want to extract from less min entropy, you need a new reduction technique. So in our second construction of small space extractors, we provide exactly such a technique by showing that there is a reduction from small space sources to affine sources. So we'll focus on that now. So an affine source is a random variable. An affine source with min entropy k is simply a random variable that is uniform over some k-dimensional subspace of F2n. And there's an alternative definition. We can say that this is an affine source if there exists linearly independent vectors v1 through vk in F2n and some shift vector b, such that our affine source is just a random linear combination of these independent vectors shifted by b. So affine sources are a very well-studied model in which to examine randomness extraction with some really interesting connections and complexity. And there are actually a lot of interesting connections between affine sources and sampleable sources. So in 2011, Viola showed that circuit sources are reducible to affine sources. And in this work, we help complete the picture and show that small space sources are also reducible to affine sources. And it should be noted that affine sources themselves are actually sampleable sources because they can be sampled by a linear circuit. So let's focus on our reduction now from small space sources to affine sources. Our reduction will actually go through an intermediate model, which we call a sequence source. Now, a sequence source, a k-sequence source, is simply a random variable that consists of k independent chunks, each guaranteed to have min entropy at least 1. But the catch is they might have different lengths, and you actually don't know what these lengths are. So it might look something like this. So the first step in our reduction is to show a reduction from sequence sources to affine sources. And then we show a reduction from small space sources to sequence sources. So the first reduction actually is not too difficult to do using some standard tips and tricks. So we'll focus on the second reduction in this talk. So now we'll reduce small space sources to sequence sources. So to do so, recall that if we have a small space source and we fix a sequence of nodes across R layers, then we can show that our small space source is actually a convex combination of independent sources. So our reduction from small space sources to sequence sources will start off in a similar way. Okay, so first we'll start by setting aside some parameter gamma that we'll fix later, and we'll want this. This will end up being such that our source is a convex combination of gamma sequence sources. And the first step in our reduction is we're going to go ahead and we're going to fix 2 gamma layers about equal width apart. And as we know from before, this shows that X is a convex combination of independent source sequences, each of length 2 gamma. And maybe they look something like this. And by the entropy chain rule, we know that the entropy of the source does not decrease that much. So now the idea is let's go and look at the gamma most entropic sources that we produce. So to make the picture pretty, let's assume they appeared on the right here. Now, what we're going to do is this sort of win-win analysis. We have 2 possible cases. The first case is that each of these entropic sources has min entropy at least 1, in which case we're actually done. Our sequence of independent sources is actually already a gamma sequence source. In the complementary case, perhaps one of these entropic sources has min entropy strictly less than 1. But if this is the case, because we selected the most entropic sources to look at, the remaining gamma sources are also guaranteed to have min entropy less than 1, meaning that all of the entropy left in our source after the fixings must be highly concentrated in those entropic sources. And in particular, if we just examine this chunk on the right here, the entropy rate will almost double. So the idea is in case 2, what we're going to do is recurse. And we argue that eventually we must hit case 1, because otherwise the entropy rate will grow so high it'll exceed 1, which is of course a contradiction. So given our reduction, all that remains is to apply the excellent affine extractor from Shin-Lee, which can handle just polylogarithmic min entropy. And we get our low entropy extractors for small space sources. So that finishes our overview of results. So we constructed 2 new and improved extractors for small space sources, and we constructed several intermediate objects, such as improved extractors for adversarial sources, explicit extremal designs, and a new reduction from small space sources to affine sources. So given all of these interesting intermediate objects, a lot of open questions remain. So that concludes my talk. Thanks for stopping by, and I hope you enjoyed.